Horseshoe bats. Horseshoe bats, genus Rhinolopus, emit sounds from their nostrils and then listen to the frequency of the sound reflected from their prey to determine the prey's speed. The horseshoe that gives the bat its name is a depression around the nostrils that acts like a focusing mirror, so that the bat emits sound in a narrow beam like a flashlight. A rhinolophus flying at a speed v-bat emits sound of frequency f-bat. The sound it hears reflected from an insect flying toward it has a higher frequency f reflected. Show that the speed of the insect is v insect equals v times f reflected v minus v bat minus f bat v plus v bat divided by f reflected v minus v bat plus f bat v plus v bat, where v is the speed of sound. If the frequency of the bat is 80.7 kHz, f reflected is 83.5 kHz, and v bat is 3.9 meters per second, calculate the speed of the insect that would be detected by the horseshoe bat. Okay, so the bat is moving with a speed v bat towards the insect, and the insect is moving towards the bat with v insect. So the source is the bat first, and the observer is the insect. So the insect is detecting the sound created by the bat. So the frequency detected by the insect, f insect, will be a frequency generated by the bat multiplied by this scenario. We have the Doppler shift. The frequency should increase as v plus v observer, v plus v insect, divided by v minus v source, v minus v bat. So that's the scenario. Observer and source are moving towards each other. This is the frequency detected by the insect. Okay, now the bat is again moving towards the insect with a speed v bat, but now bat is the observer. Bat is observing the reflected sound from the insect, and the insect is moving towards the bat with v insect and acting as the source of sound waves which are reflected. So the frequency reflected that will be detected by the bat will be frequency generated by the insect, which is the frequency detected by the insect when the bat produced a sound, multiplied by, again, we have the same scenario, v plus v observer, so it's v plus v bat divided by v minus v source, v minus v insect. Okay, so what happened here is the bat generated a sound. It was detected by the insect as this frequency, which is reflected and traveling towards the bat now. So this frequency will be Doppler shifted again as f reflected, detected by the bat as the observer. So we see that f reflected is equal to frequency detected by the insect. So we have to put this for frequency detected by the insect. It will be f bat times v plus v insect divided by v minus v bat. That is f insect, and multiplied by this v plus v bat divided by V minus V insect. So that will be the frequency detected by the bat when the sound is reflected from the insect. So now, in order to determine the speed of the insect, we have to isolate V insect from this equation. So if we take these two terms to the left hand side, we will get F reflected times V minus V bat times V minus V insect is equal to F bat times V plus V insect, V plus V bat. V plus V insect, V plus V bat. Okay, so if we distribute this, we have for the first term here, F reflected V minus V bat times V, and then F reflected V minus V bat times V insect. So we have F reflected V minus V bat times V minus F reflected V minus V bat times V insect. This is equal to F bat V plus V bat times V. So V plus we have V plus V bat times V times F bat, and then we have the second term plus F bat times V plus V bat times V insect. Okay, now we will collect all the V insect terms on one side. So we have this term and this term collected together on the right hand side, and this term will go to the left hand side. So we will have F reflected V minus V bat times V minus F bat V plus V bat times V must be equal to V insect times F reflected V minus V bat plus F bat V plus V bat. So if we take this to the left hand side, so divide the left hand side with this, we will have V insect. So we have our final answer. V insect is equal to V times we have F reflected V minus V bat minus F bat V plus V bat, and then we have F reflected V minus V bat plus F bat V plus V bat. So this will be the detected speed of the insect by the horseshoe bat. Let's compare it to the answer given here, V plus V insect. So let's see, F reflected V minus V bat, F bat V plus V bat, F reflected V minus V bat minus F bat V plus V bat, and then here F reflected V minus V bat plus the other term, and that's exactly what we get multiplied by V. Now in part B we will substitute some numbers for the speed of the insect detected by the bat. We have the propagation speed of sound in air 343 meters per second at 20 degrees Celsius, and then we will put some numbers for F reflected 83.5 kilohertz, 10 to 3 hertz, 343 minus V bat, which is 3.9, minus 80.7 kilohertz, 10 to 3 hertz, 343 plus 3.9, divided by 83.5, 10 to 3, 343 minus 3.9 plus 80.7, 10 to 3, 343 plus 3.9. And so we find the speed of the insect to be, from this calculation, 1.5 meters per second. Okay, so in this problem we have a horseshoe bat who has an interesting depression around the nostril that acts like a focusing mirror. The bat emits sounds in a narrow beam like a flashlight. The frequency emitted by the bat will be detected by an insect flying toward it. So the rhinopolis is flying at a speed v bat, and there's an insect flying toward it at a speed v insect. And the sound the bat hears will be, first of all, Doppler shifted sound that the insect hears, and the Doppler shifted sound of the reflected wave. So we will have twice Doppler shift. The insect as an observer will feel a frequency that is Doppler shifted due to an observer moving towards a source, source moving towards an observer. And then for the reflected waves from the insect acts as a source, the bat acts as an observer. Now the second Doppler shift comes. So we want to know the speed of the insect. For the source moving towards observer, observer moving towards source, we have the correct Doppler shift formula, V plus V observer divided by V minus V source, because both of these effects are acting to increase the detected frequency. If the source is moving towards observer, the wavelength is decreasing. If the observer is moving towards the bat, the detected speed of propagation speed of the waves is increasing. We have this formula, and this will be applied twice. We will just change the roles of the observer and the source. So first the source is bat, second the source is insect. First the observer is insect, second the source is bat. So if we have for the double Doppler shift, the frequency of the reflected wave that's detected by the bat is original frequency times these two terms. So we have to isolate V insect. When we do so, we obtain the relationship given in the problem statement. Now we will substitute frequency of the bat, reflected frequency, and V bat into this expression, and we can find the detected speed of the insect, numerically 1.5 meters per second.